Today we start Chapter 2, Section 4, Absolute Value in Open Sentences. And for the first time, we actually are jumping into one of the California State Algebra 2 standards, Standard 1.0, which students need to know how to solve equations and inequalities involving absolute value. And that is our goal today as well. So let's start out with our definition of what absolute value is. I know maybe in previous math courses or your previous understanding may think of absolute value as to make something positive. Here's the official definition. It's important you know it consists of two parts. It says for any real number x. Now, we say that the absolute value of x is x if what we started out with is a non-negative number. Translation, if it's positive or it's 0. Then, if for some reason the number we start out with, x's opposite, is a negative number, taking the opposite of a negative number makes it positive as well. So the basic end result is we want to guarantee that something is positive. It's how we get there. If something starts out as positive, we don't need the absolute value signs. We just keep it positive. If something starts out as negative, to make it positive, you take the opposite of it. So that's the official definition of absolute value. When we put absolute value with an equation, an equality or an inequality, they're compound sentences just as we did in our previous section. They're either conjunctions with the and or disjunctions with the or, and here's how it's listed. Here's how we can remember them. So what we know is that if you have the absolute value of some expression involving an x or a variable, if that's equal to something, it's an or sentence or a disjunction. If the absolute value is greater than, it's an or sentence and disjunction. Remember that the disjunctions are like the union of two sets. So when we go to graph our answers, when one of them has it or the other one has it, we want it all. If the absolute value is less than, it's an and sentence, and that's a conjunction, and is like the intersection of two sets, or where the two graphs overlap what they have in common. Now, just EO, LA, GO, here's just a little way to remember it. Equal to is an or, absolute value less than is an and, GO, greater than is an or. So EO, LA, GO. Equal is or, LA, less than is and, GO, greater than is or. Alright, with that in mind, let's start solving some of our examples. Let's start with example 1. We have the absolute value of 5x minus 4 is equal to 11. So the first thing we need to determine is that it's an or sentence. And we need to break our problems down into two cases. The first case, according to the definition, is when it's non-negative, meaning it's positive or it's 0. According to the definition we just saw, and let's scroll back to see that very quickly, if we start out with a non-negative number, we don't need the absolute values, we just drop them off. If we start out and think it's a negative number, we just take the opposite of it. So that's what we're going to do in both of these situations. Now, we don't know whether it's positive, 0, or negative, but if we solve for all the possibilities, then we'll have our answer. So let's take a look at that. Let's break it into the case where it's positive or 0. If the expression 5x minus 4 is positive or 0, we don't need the absolute values. We just drop them off because it represents a positive quantity. In the other case, when 5x minus 4 might represent something negative, according to the definition, we take the opposite of it. Taking the opposite of it will make it positive. So here's my two cases. The case where I think it's positive or 0, drop off the absolute value. If I think it's the negative case, I take the opposite of what was in absolute value signs, put in parentheses, take the opposite. All right, let's solve each one separately. Add 4 to both sides on the left. 5x equals 15. Divide both sides by 5, and x is equal to 3. Over here, let's distribute out this opposite symbol. So we get negative 5x plus 4 is 11. Let's subtract 4 from both sides. Negative 5x is equal to 7. If we divide both sides by negative 5, then we get x is negative 7/5. And there's our two cases. We have x equals 3 from the positive or 0 case, or, since it's a disjunction, x equals negative 7/5. We need to graph our solution. So to graph our solution, we start with the number line. We put a closed circle at 3 because there's an equal sign. So way out there at 3, we have a closed circle. And then we have another closed circle at negative 1 2/5, or negative 7/5, which is approximately there. There's no less than, there's no greater than, it's just equal. So that's going to be just 2 points on the number line. And that's my solution. Or if one of them's got it, you want it. If the other one's got it, you want it. Our graph of our solution is just those 2 points. All right, let's look at another one. This time we're going to put in a less than. Solve and graph the absolute value of 3x minus 2 is less than 4. To do that, the less than is an and sentence. E-O-L-A-G-O. So LA, less than, is an and sentence. Again, in the positive 0 case, we're assuming that 3x minus 2 is positive or 0. So we don't need the absolute value signs. We just drop it off and solve. Now, assuming, we can't just assume unless we take all the cases. So the other part of this, part 2 of the definition, is if we think it was a negative expression, that 3x minus 2 represented something negative. In that case, we replace the absolute value signs with parentheses and take the opposite of it. All right, let's solve each one. On the left inequality, let's add 2 to both sides. And also on the left, let's divide everything by 3, and we have x is less than 2. The inequality on the right, let's distribute out that negative symbol. So that's negative 3x plus 2 is less than 4. Subtract 2 from both sides. Negative 3x is less than 2. We need to divide both sides by negative 3, which changes the direction of the inequality. So instead of a less than, it becomes a greater than. And it's an and sentence, so let me try to put them together in shorthand and see if this really works and is true. So let's cover over both parts and see what we get. So for one of the parts, let's just check. Here we have x is less than 2, and we have x is less than 2, so that works out. For the other inequality, here we have x is greater than negative 2/3, x is greater than negative 2/3. So this is one of those situations where the shorthand notation does work. Again, from a previous lesson, I told you I liked the shorthand notation because when it's time to do the graph, we pretty much have everything laid out for us. We have 2 without an equal sign, so we're going to want an open circle around that. We have negative 2/3 without an equal sign, so we want an open circle around negative 2/3, and it's going to be everything in between that we graph. So not including 2, everything up to it. Choose a point, label it negative 2/3, not including negative 2/3, everything up to it. X is in the middle, so we want all the points in the middle. And that's our solution and graph of our absolute value inequality. And again, the less than was an and sentence. Let's look at another one. We have a greater than. So the absolute value of 4x plus 2 is greater than or equal to 6. Greater than is an or sentence. So we'll start out with or. Our two cases, in the positive 0 case, we are considering that 4x plus 2 represents a positive number or a 0, in which case we don't need the absolute value, we just drop them off. The other part of the definition says that consider the possibility that 4x plus 2 could represent a negative quantity. So in that case, turn the absolute value into parentheses and take the opposite of it, because the opposite of something negative is something positive. All right, let's start solving the inequality on the left. We're going to subtract 2 from both sides, and 4x is greater than or equal to 4. Divide both sides by positive 4, x is greater than or equal to 1, and we finished on the left. On the right, distribute out that opposite symbol, so that's negative 4x minus 2 is greater than or equal to 6. Add 2 to both sides. We have negative 4x is greater than or equal to negative 8. To get x by itself, we need to divide both sides by negative 4. And dividing by a negative, be very careful, changes the direction of the inequality. So it's no longer greater than or equal to, but now it's a less than or equal to, and x is less than or equal to -2. It's an OR sentence. There is no shorthand for OR sentences. But what we need to do is turn this into a Kodak moment, take the picture, graph the answer. So I recommend we take a look at this. Here's one situation. X is greater than or equal to 1, meaning we want a closed circle at 1, and greater than on the number line is everything to the right. Then x is less than or equal to -2, means we want a closed circle at -2, and less than is everything to the left of the number line. And there's our solution, and there's our graph to the absolute value inequality. All right, let's look at one other, the last one for today's lesson. This one's a little different. We don't have the absolute value by itself. It's important that the very first thing you do is to isolate what is inside the absolute values first. Get the absolute value by itself. Don't distribute the two out. Let's get the absolute value by itself, so that means we have to undo addition by 11 and undo multiplication by 2 so we can get the absolute value by itself. All right, so starting in that process, let's subtract 11 from both sides. That's going to give us 2 times the absolute value of 2x minus 7 is 14. So to get the absolute value by itself, we have to undo multiplication by 2, and that's accomplished using division by 2. And now, finally, we have the absolute value sign, everything in it, by itself. The absolute value of 2x minus 7 is equal to 7. And now that we've isolated the absolute value, we are ready to continue to solve this in the way that we've solved everything else. So it's an equal sign, absolute value equal, so that means it's an OR statement. The definition says consider two cases. One case covers positive numbers and zeros. In that case, you don't need the absolute value signs, just leave them off. Rewrite your inequality or equation in this case. The other part of the definition said consider 2x minus 7 could represent something negative, so turn the absolute value into parentheses and take the opposite of it. All right, let's solve each one of these independently. Let's add 7 to both sides. So 2x equals 14, or x equals 7. Then, with the equation on the right, let's distribute out that negative sign, take the opposite. So that's negative 2x plus 7 equals 7. Subtract 7 from both sides, so negative 2x equals 0. Divide by negative 2, and 0, of course, divided by anything is 0. And it's still an OR statement. So x equals 7 or x equals 0. For the graph, it's an OR. If one of them's got it, you want it. If the other one's got it, you want it. There's no greater than or less than, so it's just including these 2 points. So we want a closed circle at 7 and a closed circle at 0. And that's our look at solving absolute value equalities and inequalities, and the first standard from the California State Standards from Algebra 2.